There are ways that you can also measure the spring constant in a dynamic way, which is actually very interesting. I have here a spring, and this spring, this is x equals 0, and I attach now to the spring a mass, m. This has to be on a frictionless surface, and you will see when I extend it over a distance x that you get your force, your spring force, that drives it back. We have, of course, gravity, mg, and we have the normal force from the surface. So there is in the y direction, there is no acceleration, so I don't have to worry about the forces in the y direction at all. If I let this thing oscillate, I release it, it will start to oscillate about this point back and forth. Then, as I will show you now, you will find that the period of oscillation, the time for one whole oscillation, is 2 pi times the square root of the mass m divided by the spring constant k. I will derive that. You will see that shortly. In other words, if you measured the period and you knew the mass, then you can calculate k. Alternatively, if you knew k and you measure the period, you can calculate the mass, even in the absence of gravity. I don't use gravity here. So a spring always allows you to measure a mass, even in the absence of gravity. The period that you see, the time that it takes for this object to oscillate once back and forth, is completely independent of how far I move it out, which is very non-intuitive, but you will see that that comes out of the derivation. There is no dependence on how far I move it out. So whether I oscillate it like this, or whether I oscillate it like this, as long as Hooke's law holds, you will see that the period is independent of what we call that amplitude.